Okay, section 12.4 is about probability distributions. How are these probabilities distributed? And specifically, if you look here at the learning target, we're talking about defining probability distributions to represent experiments. In other words, we're trying to understand what are the probabilities of different events and how are they distributed. For instance, they give two models here in this example of having three kids. Mr. and Mrs. Mason have three kids. Now, that is a weird experiment, right? We're just going to randomly tell this couple, hey, you're going to have three kids. And let's figure out the probability of what you're going to have. Well, it is definitely not like Model A. There's not like a 25% chance that you're going to have 0 girls, 1 girl, 2 girls, and 3 girls. It's not like there's just 4 options here. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8 options, right? Because you literally have 2 options for the first kid, 2 options for the second kid, 2 options for the third kid. That is not a combination. That is not a permutation. Well, to be honest, it would be the multiplication of 3 combinations, but I'm not worried about that right now. So it's based on the fundamental counting principle. So you end up with 8 different options. So I've kind of written them out. For instance, girl, girl, girl. That's 0.5. You have a 50% chance of having a girl the first time, a 50% chance of having a girl the second time, and a 50% the third time. That really amounts to 0.5 times 0.5 times 0.5, which is 0.125. So we have a 12.5% chance of having 3 girls. Well, you could do the same thing following the route for the boys, all 3 boys, 12.5%. And every single one of these in the table ends up being 12.5%. But as you can see, come on, switch to a different color. The 3 options, which are 2 girls, whether the boy comes first, second, or third, they would each also have 12.5%. But see, those things can't happen at the same time. So there's no overlap. Therefore, you can add them together and you can find out that having 2 girls and a boy, you have a 37.5% chance of that happening. Okay? Now, well, isn't that the same for 1 girl and 2 boys? You better believe it. There's also a 37.5% chance. So we have 12.5% of having all girls, 12.5% of having all boys, and 37.5% chance of 2 girls and a boy or 2 boys and a girl. So that adds up to 100% and takes care of all of the possible options. Let's move on to example 1. One more thing to mention here about the situation we're dealing with. This is not an experiment. That would be really, like I said before, that'd be really weird to call it an experiment, okay? This is what we call a sample space, okay? Which means this is not an experiment. This is what we call theoretical probability. When you're dealing with a sample space, which means we know all possible outcomes, and we can tell you exactly what the probability of every single outcome is, then we are dealing with a sample space, not a theoretical probability, or which is a theoretical probability. It is not an experiment. We didn't just randomly tell these people, hey, you're going to have 3 kids. That would be weird. Plus, I'm pretty sure that would be fairly unethical. Okay, now if you move on to this situation, it says develop a theoretical probability distribution. Okay, this is an experiment. Okay, we're trying to figure out what the sample space is, so we're going to do an experiment. We don't know what the sample space really is. I mean, we can make some assumptions, and you can see down here that they say a theoretical probability is based upon assumptions rather than on experimentation. Okay, that's what we did on the last one. But let's see here. Teo and Henry are running for president of the student council. You will select a campaign button at random from the box, and it has 3 Teo buttons in it and 3 Henry buttons in it. You will record the number of Teo buttons. Now remember, we're only recording the number of Teo buttons. We're reaching in the box, we're pulling out 1. Now, it says, what's the theoretical probability distribution for the sample space? Now, why are they telling me 0 and 1? Because when we pull it out, if it says Teo, we're going to mark down 1. If it says Henry, we mark down 0. So, we're not marking down how many. So, Teo, it's either going to be how many zeros and how many ones. So we're not thinking of this in terms of Henrys and Teos. We're looking at how many Teos did we get. Okay? So, since there's 3 and 3, it says right here, the probability distribution, theoretical probability distribution for this experiment is based upon the fact that you have half in the box will give me a 0, and half in the box will give me a 1. Okay? Now you plan to select a button at random, but then put it back in the box, and then select another one at random. Okay, so you're not looking at them, you're just reaching in, stirring them around, and picking one out. Okay, you will record the total number of times that you get a Teo button in the experiment. Define the theoretical probability distribution for the sample space. And then they say 0, 1, and 2. Well, that's kind of weird. 0, 1, and 2, what does that mean? That means we're going to only draw out 2 times. So if we're going to draw out 2 times, the outcomes we could get are 0 Teo buttons, 1 Teo button, or we could get 2. And this right here is called a probability distribution. Let me type that out. Probability distribution. Now, we did something similar to it on the boy-girl example. We just, for that boy-girl example, we could have made a probability distribution really quickly. And I guess I could do that really fast. Okay, so let's suppose we only want to count the number of girls and the probability of that outcome. So we could get 0 girls, which obviously that means all boys, 1 girl, 2 girls, and 3 girls. We calculated 12.5% here, 12.5% here, 37.5% here, and 37.5% here. This all adds to, just like we talked about before, 1. Okay? You can't have a negative probability, and you can't add up to more than 100%. You can't do this. This is impossible. Es imposible. Now, we still haven't decided on this Teo example how this is going to work, but we can make a tree diagram if we wanted to. So when we reach in the box the first time, we got a 1/2 chance of getting a Teo. And when we do it again, we also have a 1/2 chance. So if you multiply those together, because you're putting it back in the box, so we already know that it's not going to change the probability. So you multiply those together, you get a 1/4. All right? That's no. Or no, that is actually 2 Teos. You can see in there, that's 2 Teos. So we would have 0.25. Well, we could do the same thing with Henry. Okay? By the way, do you notice they use T and H, heads and tails? Kind of like a 1/4. This is exactly the same thing you could do with a 1/4. or any coin. Okay, so this would be no teos. No teos. This would be two teos. And so no teos would also be a quarter. But then we got these two situations in the middle where we get one teo. Those things can be added together. So that'd be 0.25 plus 0.25. So we have a 50% chance of getting that one teo out of the bunch. And we already know that if you add up all of them together, you get 100%, because that's the total amount it could be. Now, this one, it's called, this one's a different one. It's called a uniform probability distribution. This is definitely not what we had. Okay, what we had, remember, was a quarter, a half, and a quarter, right? That was in our table that we just wrote down. I don't like the way they write their tables, by the way. That's weird. That is an example that is not a uniform table. A uniform table would mean every option is the same. Now, if you are dealing with only one, only drawing out one, right? Look what it said for select one button. That's a pretty limited table, right? You're selecting to see if you get a teo, right? But you're only drawing one out. So the two options, you either get it or you don't get it. And if you have 0 teos, that would be 50%. And this is 50%. So this is what we would call a uniform distribution, because every option, every possible option in the table is the same. Whereas the other probability distribution is not the same. Okay, so in these kind of questions like try it, no, this try it right here, you are going to be making your own little charts. I would suggest you make them like the way I did. I don't really kind of like the way they've set them up. It's just not as well organized, in my opinion. Okay, so what happens if they give me a table like this? A cell phone company surveyed 500 households about the number of smartphones they have that are in use. So we've got 0, 1, 2, 3, 4, 5, and then they have one more category called 6 or more. Then the question below says, would you, and then they measured the frequency, how many fit into each category. But you can obviously see most people had 3 smartphones in the house. Okay, that's how they ended up with one, the 144 is obviously the biggest number, okay, of the 500. It says, would you recommend that the company concentrate on selling data plans for individuals or plans for families with 3 or more smartphones? So 3 or more smartphones, that's this group over here. And then you got this group over here. So which group do you think is the better fit for coming up with, what we should be, concentrating our energies and efforts on? Well, if we add the 3 over there, 10 plus 66 plus 120, we get 196. So there's a 196 in this group out of 500. Now, what is 196 divided by 500? 0.392. 0.392. And then, of course, if we go over to the other one, 144 plus 79 plus 37 plus 44, if I total those up, I get 304, which makes a whole lot of sense because those two things have to add up to 500, which means I didn't even probably have to do this. I probably could have just said 1 minus 0.392 to get the other one, right? 1 minus 0.392 to get 0.608. But I could double check that by taking 304 and dividing it. Yes, of course I'm going to get 0.608. I mean, look at it. It's just twice 304. And that's because the denominator, all I have to do is double the top and the bottom. And then I get 608 out of 1,000. Well, that seems to make sense. Okay, let's see what they did in their explanation. Define an experiment, okay? Define an experimental probability on the sample space, which is what they did already. First, divide each frequency by 500. Okay. Folks, you don't have to do this in the order they chose to do it, but you can. Ain't nothing wrong with what they did. So they divided every one of these divided by 500. And what they ended up with was 2%, 13%, and 24%. What does that happen to add up to? 39%. Now we know it's not quite that, but it's close. And then over here, they added these up and they got 61%. We know it's not quite that, but it's close. And so which one would you concentrate on? Probably we get a lot more family plans, you know. So graph the probability distribution? We could. Why? An experimental probability distribution for the experiment is a function. All right, so we could graph this. All right, these are the bars that add up to 61%, and these are the bars that add up to 39%. So why would I want to create a bar graph? Sometimes people find it more useful to have a bar graph than they do to just use the raw numbers. I don't know. But we have already established 39% for the lower group and 61% for the upper group. So obviously the company should probably focus on the family plans rather than the individuals. At least that's what I would do. Now, a binomial experiment, which is kind of what we had with the Teo and Henry example, is an experiment that consists of a fixed number of trials. That's very, 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 very important. With the following features. Each trial has two possible outcomes. We usually call them success and failure. So, one example is shooting free throws in basketball. You either going to make the shot or you're going to miss the shot. So it's one or the other. The results of the trials are independent events. In other words, making one free throw does not determine the next probability that I'm going to make the next free throw. Like flipping a coin. Getting heads does not change what's going to happen the next time I flip the coin. The probability of success is the same for every trial. It does not change. So this is obviously, we are not talking about, so if you were going to be talking about pulling marbles or pulling buttons out of a box, you have to be putting it back in every time. You cannot talk about, there's no binomial experiment if the probability keeps changing. Okay, that's just not possible. So, binomial experiment, fixed number of trials, has to have these three stipulations have to be true, okay? But this is kind of another one. It's very, very important that you have a fixed number of trials. Okay, is the experiment considered a binomial experiment? This spinner is spun 3 times. Assume that the spinner is equally likely to stop in any of the sections. Success is landing on a section marked go forward 2 spaces. Okay. Go forward 2 spaces. Okay, I see that here and I see that here. Okay. So, well, how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8. We got 8 of them. All right, so the probability of going forward is 2 out of 8. And yes, folks, I know that's 1/4 or 0.25. So every time we spin, we've got a 25% chance of getting it on one of those spaces. We'll just consider those, together, so to speak. The outcome of one spin does not affect the probability of another spin. Yeah, this does qualify, because we're spinning it 3 times, so that's a fixed number of times, right? Fixed number of times. And it goes through and it meets all the criteria. It either lands in one of those spaces or it doesn't, so that's like success, failure, that kind of thing. Okay? In a class of 23 students, 7 students completed the term project. 2 students selected at random half to give presentations. Dang. Success is that the student has completed the project. Okay. The probability that the first student has completed the project is 7 out of 23. If the first student completed the project, the probability that the second student is 6 out of 22. Those are not the same. Okay? If the first student was a no, the probability is 7 out of 22. Because the probabilities for each trial are different, the experiment is not a binomial experiment. I bet there's going to be a question on your test where you have to decide if it meets the criteria of a binomial experiment. Is there a way to find the binomial probability using a formula? Well, there is, okay? And this is the formula. Oh, look, a combination, right? Now, P represents the probability of success. So P is the success probability. So, let me give you an example. I'm going to shoot 25 free throws. And I want to know the probability that I'm going to make. Now, this is making exactly. That's a key word here. Exactly. Let's see here. I'm a 25, let's see, times. Okay. I'm going to say, what's the probability of making exactly 31 free throws? Okay. Now, what's my probability of 31 free throws? How in the world could I do that? Oh, because I typed wrong. Sorry. That sounds dumb. 20. I meant 20. I'm like, how can I make 31 free throws when I'm only shooting it 25 times? That would be a trick, folks. Okay. Of making exactly 20 free throws. So if I'm using this formula, you have to know my probability of success. I'm an 80% free throw shooter, and I'm going to make 20 of these. That means 20% of the time I fail. And if I made 20, then that means I missed 5, right? Because I shot a total of 25 times. So if I use my formula, my calculator, 25 using the NCR 20, and then, and then I have 0.8 to the 20th, and 0.2 to the 5th. I get 0.196. Now, you might look at me and go, Mr. Staley, you're telling me there's less than a 20% chance that you're going to make 20 free throws? Well, folks, that's where it comes back to this definition here. Exactly 20 free throws. I might make 21 free throws. I might make 22 free throws. I might make 19. I might make 18. I might make 17. In other words, there would be you remember we talked about probability distribution chart like we did before? Well, I'm talking about missing all the free throws, making one free throw, all the way up to 24 free throws, 25 free throws. That's a long list of numbers, and we know that all of those numbers have to add up to 100%. So I, in the middle of this chart, was asking about 20 free throws made, and that number in that particular block is 0.196. Now, there's a reason why I chose that particular number, because if I had chosen like 24, let's just do it with 24. I'll repeat the same exact process, but I'm going to change it for 24, which means I've only missed one stinking free throw. But I made 24 free throws. I have a 2.3% chance. I have a very small probability chance that I'm going to make 24 out of 25. Is it possible? Yeah, it's possible. Not very likely that I make exactly 24 free throws. So if people are betting money on exactly 24, that's, you got like what, 26 different possible outcomes? I could make 0 free throws all the way up to 25 free throws, but that's 26 different options. No wonder I'm as a possibility I could lose all my money. Very, very good likelihood of that. Okay, in example 4 here, we have a grocery store gives off scratch-off cards with a purchase of more than $100. So this isn't exactly a lottery, so don't equate it to that. It says Terrell has 5 scratch-off cards. We spend money at the grocery store. What is the probability that he has exactly 3 winning cards? Now that's exactly. Eventually, we'll get to this idea of 3 or more cards, which we'll see if they do that. And if not, I might throw that in there just for kicks and giggles. He has exactly 3 winning cards if each card has 30% chance of being a winner. First, we want to know if this is a binomial situation. Well, Terrell has 5 cards. That's a fixed number of trials, right? Each card is either a winning card, success, or not, success or failure. Whether one card is a winning card does not affect the probability, that's independent, right? That the next card is a winner. Probability of success is 0.3, same for every single card. That does fit. This is a binomial experiment, okay? So now they want to use the binomial formula, right, to figure out what we're doing here, right? So the probability of getting exactly 3. Now, they didn't make a whole probability distribution out of this, but we could. And in fact, with the second part I'm going to ask here, we're probably going to have to do some of it. So we've got this one, the combination right there at the beginning, 5C3. And then we have probability of success. We got 3 cards. And then the probability of failure, we have 2 cards. Now, I wouldn't look at this top line because it gets kids all confused. You just need to realize that these two have to add up to 100%, and these two have to add up to the number of trials. And then you let the calculator do the work. So the probability of getting exactly 3 winning cards is about 13%. What about... I don't know that they're going to do this, so let me check ahead. So they don't do it in a future problem. I wish they did. The probability of 3 or more. Okay, now that basically means you're going to have to do 3 and 4 and 5 and then add them together. So you would have to do this 3 times. Okay, so I'm going to jump over to Desmos and do it with you. Okay, so you can see over here on my Desmos, I did the first one. Well, we know that's like 13%. And then I did the second one, which is, of winning exactly 4. Obviously, that probability is going to be lower. And then I did the the third one, which is probability of winning all 5 of them, which has got to be lower than that. When you add those 3 things together, look what we get. 16.3%. Wow. So, what does that mean that each one of these individual parts is? Look how low the probability of getting all 5 of them is. Which means getting 4 of them is like, yeah, 2.8%. So those are low, right? Those extra 2 that I added on, not very likely. But that's what I would do if I had to do all 3 of them. And that's all we have for these notes. You guys have a great day, and we'll see you soon. Well, I slightly lied. There's a really good picture on the next page, which just kind of shows you what a uniform distribution, what a non-uniform distribution looks like, and then talks about, just summarizes the binomial experiment. Okay, so that's a good looking picture to kind of help, see what those 2 different distributions look like.